Everybody. Thank you all for being here. We have a relatively large group today, and I just want to start by acknowledging and thanking OPM and Joanna Wozniak-Brown for organizing this event, which is part of the second annual Connecticut Sustainability and Resiliency Week. My name is Nicole Govert. I'm a community resilience planner with CIRCA, which is the Connecticut Institute for Resilience in Climate Adaptation. CIRCA is a research institute based out of Yukon Avery Point, and the mission of CIRCA is to increase the resiliency and sustainability of Connecticut municipalities to the impacts of a changing climate. As I was saying this, I hope somebody counted the number of times I said resiliency and sustainability in about 2 sentences. I'm joined today by a couple of my colleagues, Jim O'Donnell, he's the executive director of CIRCA, Marc DeVos, a research associate at CIRCA, and Mary Buchanan, who is the other community resiliency planner at CIRCA. Before I hand it over to Jim and Marc to begin the presentation, which will be an update on the Connecticut Climate Report, I just want to go over a couple of housekeeping things quickly. And Marc, you can switch to the next slide. We will be recording this webinar. I've started the recording and sending it out after the event to all that have registered. It will also be posted on CIRCA's website. Because we have such a large group today, you will not have the ability to unmute yourself or take yourself off your camera. If you do have questions throughout the presentation, please put them in the chat. Mary and I will be monitoring the chat and trying to answer any of the questions that we can along the way. And then we'll be selecting some questions at the end to ask Jim and Marc. And we'll also be putting their contact information in the chat at the end, that if you have any questions, you can reach out to them directly. So with that, I'm going to hand it to Marc and Jim.
Hey, good morning. This is Jim O'Donnell. Can you hear me?
Yeah, yep, sounds good.
Okay, great. So thanks everyone for participating today. This is a seminar that we want to present to get some feedback. There are 3 sections. There'll be an update to the climate change report that Angie Seth and colleagues at Yukon developed 2019, which described at that time the outlook based on the climate models available at the time for changes in climate in Connecticut. And then I'll be updating the sea level rise report that I submitted in 2018. Basically, there's more data there, and there are new global climate model results to share and to assess for their relevance in Connecticut. Then at the end, we'll hopefully be able to take some questions and receive some feedback from the audience. Okay, Marc, when you take the next one.
All right. Good morning, everybody. Marc DeVos here. Can you hear me okay? Nicole?
Yep.
Okay, great. All right. So just to set the scene in terms of the information and data landscape, this project to assess whether we can derive new information about climate extremes in Connecticut is rooted in the CMIP6 or the IPCC data and information landscape. That whole ecosystem is inherently a United Nations climate change project. Under the United Nations Climate Change Project, you've got the World Climate Research Program and CMIP, which I'm sure a lot of you have heard of, and people tend to, use the acronym CMIP interchangeably with the IPCC and so on. But CMIP is actually just one project of the World Climate Research Program, which itself is part of the UN. And CMIP stands for the Coupled Model Intercomparison Project. Coupled there means that we now have an understanding that it's important to consider both the ocean and the atmosphere and, for example, land use processes, because they all feed into the weather and climate that we experience, and they all interact with each other dynamically. So it's no longer sufficient to simply have a weather model or an atmospheric model. You need all of those components, hence the coupled. And within CMIP, there's a whole range of experiments going on. And one of those experiments, which is probably the one that you're familiar with when you think about the IPCC, is called the Scenario MIP, the Scenario Model Intercomparison Project. And the scenarios there are emission scenarios and climate change mitigation scenarios and so on. the point here is just that scenario MIP is just one activity of CMIP, and people are looking at lots of different aspects of the changing climate as part of that CMIP initiative. So what are the scenarios in scenario MIP? I've kind of abridged this slide, but basically the scenarios are made up of two major components. The first component is a radiative forcing component. So that you would have been familiar with as of CMIP 5, which is how much radiation is arriving at the top of the Earth's atmosphere. And you would have maybe heard about radiation scenarios like RCP 4.5 and so on. So a measure of the radiative forcing. But in CMIP 6, we developed this appreciation that there are socioeconomic aspects to this as well, and they will in turn affect the lived experience. And so they introduced the so-called SSPs, or socio-economic pathways. And so the scenarios that are now being modeled in scenario MIP are a combination of the radiative forcing pathways and the socio-economic pathways, which describe, the appetite of governments for mitigation. They describe things like land use policies and so on. And there's a sophisticated process of combining those two aspects via things called integrated assessment models. And once you've combined those two processes, you get the CMIP 6, or the 6th generation coupled model scenarios. There's a whole range of those scenarios, different emission pathways, different appetites for mitigation and adaptation. Too many basically to analyze in this setting. So we focused on two, so-called SSP 2-4.5, which is, you can think of as a sort of middle of the road or business as usual-ish kind of pathway. You can read the text there if you're interested. And SSP 5-8.5, which represents a kind of worst case scenario, so low adaptation and mitigation interventions and high radiative forcing, to kind of give us a spread of the range of plausible outcomes by the end of the century. If you're interested more in the details of the scenarios and how they develop them, there's an open access paper published in an EGO journal up at the top right. Okay, so obviously an important aspect is localizing climate projections. We all have a fairly well-established understanding of how things are likely to change at the global scale and even the regional scale, but what does that mean for the local climate, Connecticut scale, or indeed town scale? And so what you see there is this representation that climate models work by solving physics and chemistry equations in little blocks. We split the Earth up into these little blocks or cells. And what you can immediately see is that the more blocks or cells you use to split the Earth up into, the finer your picture of the Earth will be. And the analogy here is like an old pixelated photograph from your 2003 mobile phone versus a nice sharp photograph taken with today's iPhone. The reason why we don't just use infinitely many cells is, of course, because there's a computational overhead there. So supercomputers can only crunch so many calculations, and so it's a trade-off between resolution and computational cost. Now, at the global scale, each of those little blocks represents somewhere in the region of 100 to 150 kilometer square blocks, which is probably too low to discriminate spatial patterns within the state. And so for this project, we looked at a range of so-called downscaled climate projection products, which is where you take the global product and you add information to it from measurements and real-world observations to try and improve the spatial fidelity of the information. So for Connecticut, if you were to take a global resolution climate model, those four little cells that I've indicated with these dots here, those are the four locations for the state using a typical global climate model where you would have genuine information. Those 4 points is where you would be solving the equation. And clearly that's not really enough to tell whether there's going to be a difference in Hartford versus Bridgeport, for example. So the products that we selected come from 3 different groups. They come from NASA, a project which I've referred to here as EvoFlood. It's a European initiative with UK and European consortium partners. And then in the bottom right here, the Oak Ridge Laboratory also had a project, and they improved the spatial discrimination ability of these climate projections by adding and combining them in sophisticated statistical ways with measurement data. And so the idea is hopefully we get a slightly finer photograph of the state than the pixelated view that we get from the global products. Those are the details of the downscaled products that we used from the 3 groups. I don't think it's important to go through the minutiae there, but the information is there if somebody has questions at the end. And so for each of those products, there's a range of climate models. There are hundreds of climate models, which are part of the CMIP initiative. And we've taken an overlapping set of 4 models for each of those 3 products. So we looked at all the models that NASA used, we looked at all the products, all the models that EvoFlood used, and we looked at all the models that Oak Ridge Laboratory used, and we took an overlapping set of 4 and compared them to produce our collection of climate projections. So the collection, or the ensemble of climate projections that we analyzed for this project consists of 3 products from those 3 groups, 4 models, and 2 scenarios, the sort of middle of the range scenario and the high-end scenario that I described early on, to give us 24 possible realizations of the future climate in Connecticut. So an obvious question is, all right, so we assume that these projections are going to perform better because they have higher spatial resolution of the state. Is that true? And so the idea that we had to answer this question is to lean on the data from the airports around Connecticut, 7 airports. The reason why we chose those is because it's a high quality data set. They've been quality controlled and sort of archived and collected in standard and well-described fashions. So we have a fairly good idea of what's going on with the data, and we can place a high degree of trust in them. So that's what we've used to answer the question as to how reliable these climate projections are. So we use them in 2 main ways. Firstly, we use them to bias correct the climate projections. So it may be true that a particular climate projection is, for example, consistently 2 degrees too warm or 2 degrees too cold. That doesn't mean that climate projection is unusable if it is consistent in that bias. So if we determine what that bias is and then we correct that consistent bias, then there's still usable information that we can benefit from. So the first way that we use the measurements is to bias correct. And the second way that we use the measurements is to select a subset of those 24 climate projections, which do a good job of simulating the extreme statistics in the state. So we ask basically for the overlapping period that we have measurements for, did this particular climate projection produce the same sort of statistics for the extremes in Connecticut that were observed at each of these airports? And if yes, then we retain the climate projection, and if no, then we discard it. So the first kind of look at this would be to look at some long-term means. So lots of things going on in this plot, so I'll sort of unpeel it for you. This is a view of daily maximum temperatures. So daily data, the daily maximum for each day of the year, but we take 5-year means, right? So from those daily averages, we make 5-year averages. And in red, what you're seeing is that high-end scenario, so SSP 585, and in blue is the sort of middle of the road scenario, SSP 245. And in the black, which is a little bit difficult to see here, but I'm highlighting it with my pointer, is the measurements from, in this case, Hartford Bradley Airport. Also quite difficult to see are these dashed horizontal black lines here, which I'm tracing now with my laser pointer. And these are the historical bounds. So it's simply the maximum and the minimum values that we've observed throughout history at this airport. And you can see there that it just touches the upper bound of the measurements and the lower bound of the measurements. That defines where these horizontal lines go. And you can quite clearly see that for daily maximum temperatures, we're seeing a fairly coherent and convincing increase from sort of 1990, the year 2000, 2010, through to the end of the century. Another thing that I kind of wanted to point out, which this kind of analysis helps with, is we're not entirely sure what the emission pathway is going to be. Of course, it depends on what governments do and how much we emit. But by 2030, let's say, if you look at the blue shading, by 2030, we're exiting the bounds of what we've seen historically. So regardless of the emission pathway, it looks like somewhere between in the region of 2030, we're going to be entering a new state where we're seeing new averages that we haven't seen before. I should just clarify, the shading is the spread of all of the reliable ensemble members. So of those 24, whichever were reliable, I've shown that spread using the shading, and the heavy lines is just the average of all of those reliable members. Now, I'm going to cycle through two different locations. So this is for Hartford Bradley. This is Meriden, so kind of in the middle of the state. And you see the way the line jumped up and down there. So clearly some spatial differences, right, between Bradley, which is kind of more northerly, and Meriden, which is in the center of the state. And then if we step down again to New Haven, again, a step down. So more warming in the interior, relatively less warming in the coastal regions. And so you can start to see that, yes, it is important, the spatial, this idea of spatial discrimination, because it's not true that Hartford is going to end up being the same temperature as New Haven. You can quite clearly see that there's a difference there. Okay, so the next question is, what about extremes, right? So we're not necessarily interested in long-term averages here. We're interested in severe rainfall events or heat wave type events. And so to answer this question, we look at the statistical distributions of the climate projections and the measurements, and we're interested in, I'll explain everything that you're looking at in this plot here, but we're interested essentially in the right-hand tails of the distributions for the statisticians among us. All right, what we're looking at on the right-hand side here is for Hartford, we're looking at the 24 climate projection ensembles. There are only 12 little squares here, but that's because there are purple dots and green dots in the plots, which are the two different scenarios, 245 and 585. So there are 24 climate projections shown on this plot. And on the y-axis of each of these is the modeled distribution, and on the x-axis of each of these is the measured distribution. So the point of these plots is, if the climate projections were reproducing identical statistics to the ones that we've measured at the airport, then you would see all of these markers lying along a perfect 45-degree line. And you can see that in this case, daily minimum temperatures for Hartford, and of course we do this for various variables and in all 7 sites, these markers do kind of lie on this 45 1-to-1 line. And so we're pretty confident that the climate projections are doing a good job of simulating daily minimum temperatures at Hartford. But if we look at a different variable, in this case precipitation, what you can see here is that when at the upper end of these distributions, we're doing a pretty poor job, right? Clearly here, high rainfall events are sitting quite far away from this 1-to-1 line. And so we're not confident that the climate projections are doing a good job of simulating the precipitation statistics for extremes that we've measured, right? And obviously we quantify all of this, and we do it for all the data that we have. And so we come up at the end of all of that with an idea of the reliability of each of those climate projections at simulating each of the variables that we're interested in. And these are the results. So we got mixed reliability for maximum daily temperatures, high reliability for daily minimum temperatures, which are very important because those are the cooling periods to offset heat stress. We got mixed reliability for daily average wind speeds, low reliability for precipitation, and we weren't really able to form an opinion for relative humidity because we didn't have enough data. There were too many gaps. All right, so what are some of the implications of these increases, small increases in the mean temperatures on, for example, extreme heat events? So what we've got here are 2 extreme value curves, and let's just focus on the top one for the moment. On the x-axis here, what you've got is return periods, right? So every 5 years, every 10 years, every 20 years, every 100 years, what can you expect to see in terms of an extreme temperature? And the temperature scale is on the y-axis. You've got degrees Celsius on the left and degrees Fahrenheit on the right. And the 3 different curves, or the 3 sets of curves, the blue is the period 1980 to 2010. The yellow or gold is sort of mid-century, 2030 to 2060. And the red set of curves at the top here is late century, 2070 to 2100. And so if we focus on the 1 in 10 year event, what we can see is that the blue curves were sitting somewhere between 90 and 95 degrees Fahrenheit, right, for the 1 in 10 year event. So we could expect a 1 in every 10 years, we could expect somewhere in the region of 92-degree warm day for Meriden, right? By mid-century, that number has jumped up to just shy of 100 degrees Fahrenheit. By late century, that number is sitting up at somewhere near 104 degrees Fahrenheit. So you can see how those extreme heat days are escalating in magnitude. The other way, of course, that this works, if you read the curve in a slightly different way, is that an event which used to occur roughly 1 in every 100 years in the blue curves, which is 1980 to 2010, if you seek that same Y value or that same heat magnitude, it's now suddenly occurring every 5 years by middle of the century. So that's where you get this idea of increased magnitude and frequency of extreme events. And that's what we mean when we use those terms. Same idea in the bottom plot. We don't have to go through it, but essentially these are winter cold extremes. And you can see here that the blue curves, the historical curves, are sitting up near the top. That's because the y-axis is structured that colder is near the top and warmer is near the bottom. So these cold events that we used to get historically sitting at, for the 1 in 10 year event, somewhere near negative 9.4 Fahrenheit, are simply unlikely to ever occur again going forward with the warming that we see due to climate change. So we see actionable evidence for significant increases to extremes in daily minimum temperatures and daily maximum temperatures. We see some evidence for changes to extreme wind speeds, but it's very difficult to say with confidence what those changes will be because they're inconsistent in sign. So some areas are showing increased wind speeds, other areas are showing decreased wind speeds, and their magnitudes are kind of small. So we're not particularly worried about that for the time being. We don't see actionable evidence for changes to extreme precipitation from these daily averaged climate projections. Now, that's an important caveat because, of course, short, acute rainfall events, we understand that those mechanisms which drive those events are likely to increase. And so, yes, the risk is there. We're just not able to quantitatively show anything new with this set of climate projections. All right, so if we consider what kind of impact this could have on an everyday life situation, let's look at heat stress. So you may be familiar with the heat stress index, which is a National Weather Service and NOAA product. It basically is the real feel, if you like. A lot of people read that on their phone because the humidity in the air also determines what you experience. It's not only the temperature. And so the hotter and the more humid it is, the more dangerous it is for human beings and animals and so on. And so, we saw this kind of press release from the government pretty recently. Heat index values are expected to exceed 100 degrees, and that would activate a range of protocols that are necessary to keep people safe. Now, if we run those temperature projections forward, I've used the same colors that you would see in the heat index, but made it a bar chart with decades on the x-axis and the number of days per year on the y-axis. In this case, this is Willimantic, and you can see that these extreme danger days, the dark red, are slowly increasing in the proportion towards the end of the century. And the danger days, which is the second to last category, the orange, are also increasing markedly, as is the total number of days with some kind of heat stress indication, right? So there's this general increase through to the end of the century in heat stress. So again, small changes in magnitude of temperature averages, 2 degrees, 1.5 degrees, we hear about 2 degrees, 3 degrees, the Paris Agreement. Those make radical differences to the climate extremes that one might experience. Now, I'm going to caveat this by saying that we see in this particular plot huge variability from model to model, right? And that's largely due to the relative humidity being kind of inconclusively reliable at this point. So we are looking into more detail in that. The exact amount of increased heat stress is difficult to tie down because of this variability, but we can show quite coherently that it is likely to increase and become more of a threat across all models and places. Another way to look at that is the number of heat days. So this is for Hartford-Bradley. Each of these little bars is a climate projection member, and you've got decades on the x-axis here. And again, number of days per summer. So June, July, August is JJA. And you can see in the top plot, which is days per year with maximum daily temperature above 90 degrees Fahrenheit, there's some discrepancies between climate projection models, but quite clearly a very coherent increase in the number of days above 90 Fahrenheit through to the end of the century. The bottom is the same idea, but above 100 degrees Fahrenheit. And so you can see that we're just starting to see those days above 100 degrees Fahrenheit where we are right now during this decade. They were almost absent in the historical record, and we see quite a few of them up in the order of 5 days per summer by the end of the century. And this is for the middle of the road or medium forcing scenario. If we take that to the worst case scenario, those numbers jump up for SSP 585. That was just an example for a different location. And then I'm going to end off this section of the presentation with just some further views on precipitation, since we weren't convinced by what we saw in the climate projections. So the climate projections that we analyzed in our investigations into extremes here didn't demonstrate statistical reliability as far as we were concerned. Now, that does not mean that very well understood and very likely changes are precluded at a regional scale. All it means is that it's going to happen somewhere, but we can't show objectively that it's going to happen in Bridgeport and not Hartford, for example, or vice versa. That is because this is essentially a spatial scale problem where there's a huge sensitivity of the rainfall statistics to the track of the storm, right? So to paint an extreme scenario, the storm might pass over your backyard, but not your neighbors, and so on. And so that makes it incredibly difficult to approach this from a sort of point measurement statistical perspective. Now, why did we try and do that? Well, because we thought that these downscaled climate projections might have reached that point where they can give us that spatial discrimination. But it showed us that we haven't really reached that point yet. And so we're going to revert to what we can tell from history and from the regional analyses, which our colleagues like Rob Nazarian at Fairfield University and Angie Seth from UConn have done a great job of doing to date. So we're not able to add much new, in other words, to what we already know. We say that we're going to sort of revert to what we know in history. These slides just show that once we realized that, we looked at 3 historical or backward-looking data sets. So we looked at the hourly records, again, from the measurements at the airports. And we looked at 2 so-called reanalyses, ERA 5 and the NARR reanalysis. And what reanalyses products are, essentially think of them as a weather forecast, but a weather forecast which got corrected as the measurements became available and they reran them. So you can think of it as like a corrected weather forecast with the benefit of hindsight. And we looked at whether things have been changing, because a large criticism of NOAA Atlas 14 is that they've done a great job of this sort of hit or miss idea by spatially averaging things, but it's a stationary approach. So they're assuming that nothing is changing. And again, if we look at whether things are changing in this single location historical perspective, we don't yet see convincing convincing evidence that on a point-by-point basis, there is radical change. On the left-hand side here is a time series of hourly accumulations in inches, with time on the x-axis from one of these reanalyses products at Bridgeport. And you can see that, we had high rainfall events back here in the 50s. You can see that we get these sort of long period oscillations in any case, which may be affecting the statistics. And if we were to kind of bin these markers, because a lot of them are overlapping. So if we were to put them in little boxes and shade those boxes by the number of markers in each of those little boxes, you would expect to see, if there's an increase, you would expect to see higher density of those points. So yellow climbing up as we move towards the end of the measurement period, which we don't yet see. Now, again, that doesn't mean that things are not changing. It just means that maybe the storms all missed this particular location and therefore change is not reflected in those statistics. So we revert to the area average, which we already know. We just wanted to see if we could do better than that with precip. Here is this laid bare, this idea of the small spatial scales which are relevant. So this is the extreme rainfall event that happened in Oxford last year. And these little numbers are rainfall recordings that happened in different parts of the states. And you can see up here, we got 10 inches cumulative rainfall for that event. And I think there was somewhere with 12 over here. And if we look at that in a slightly cleaner fashion, we've got a factor of 10 in the rainfall accumulation in less than 20 miles. So very clearly precipitation varies on very small spatial scales, and the new set of climate projections that we analyze can't get us around that yet. So we have to take this approach of looking for increases, at all the stations maybe in one go, and then assuming that the risk of an event like this happening could happen anywhere in the state. We can't do better than that at this point, we don't think. And so I think that a safe perspective is, like I say, to assume that something like this could happen basically anywhere in the state. And with that, I'm going to hand over to Jim to talk about the sea level trends.
Okay, thank you, Mark. Let's jump to the next slide. So this is the summary slide from the 2018 report. There, I looked at 4 different ways of estimating what the upper bound of the likely sea level rise in Connecticut would be. And these are the 4 curves that I reported. The lowest one is the upper bound based on a projection of data. The middle 2, the yellow and orange, are based on the IPCC results from AR5 for the RCP 4.5, which is an emission scenario that's now SSP 545. Then the top curve, which is the highest potential sea level rise, was an attempt that the IPCC put together to estimate what the most physically plausible upper bound would be. And it's based on estimates of observed ice melting rates. And then the conclusion of this analysis was that 50 centimeters sea level rise above the national tidal data epoch by 2050 was the upper bound of what was plausible, and we should plan for that. And that was enacted in several state regulations. Let's go to the next one, Mark. So what I've done since then is update that. And here in this figure are the observations that have been acquired in Connecticut at the stations listed on the top right here since about 1930. I'm not quite sure why the graphic is so weird. Do you see that, Mark?
Yeah, it's got something to do with the figure's background.
Yeah. Okay. So there's obviously we knew most about this in 2018, and what the last 10 years show from like 2016 to 2024 is a rapid increase. And so in the mean sea level, all the gauges around Long Island Sound in 2014 is the highest ever. The black squiggly line here that is below the wiggly line, right? That's an analysis of the global mean sea level rise that was published in 2024. You can see still that the mean sea level in Long Island Sound is rising faster than the global mean, and there's lots of variability in it. There's a pink shaded line there which illustrates the estimate of the uncertainty in the global mean. And you can see that that width of that pink shaded area gets narrower as we go forward, as our ability to estimate the global mean gets better. And the narrower it gets, the clearer it is that mean sea level is increasing. It's higher in Long Island Sound than the global mean, and it's rising faster. Okay, next one. So then the solid black line in this graphic is the projection from the IPCC, the latest IPCC predictions for global mean sea level. And this is the average of all scenarios. And then the the shaded areas in light blue and purple are the spread amongst the ensembles for the same RCP or SSP 58545. Sorry. So this is the intermediate emission scenario. We're anticipating no CO2, substantial greenhouse gas emissions reductions until about 2050 or so. And so the red bar at 2050 shows the results of the SSP 585. That is the very few CO2 emissions reductions and there's almost identical because the sea level is going to respond the same way until about 2050. And at that point, the two scenarios diverge a little. So at 2100, which is the right side of this graph, there's a red bar, which is a little less clear, showing the upper bound of what's in 2100 is significantly higher. And so if CO2 emissions reductions aren't inhibited, then we're likely to see higher mean sea levels in 2100. But the result in 2050 is approximately the same as what we had in 2018 result. The upper bound of what's likely at 2050 is about 50 centimeters. And the improved models that were released by the IPCC in 2023 reduce the uncertainty associated with ice melting, but they don't really change the upper bound of the likely scenarios for mean sea level. So 50 centimeters, which is what we enacted in 2019, there's no strong evidence to change that at this time. Next one. So to illustrate what that's likely to mean for return intervals, I got the NOAA return interval diagram for water level at New London from their website, and currently the 10-year return level is about 3.7 feet at New London, but if mean sea level was 24 inches higher, let's go down one. Then that level, 3.7 feet, would be reached with a probability of 27%, which is approximately a 3.7 year event. Okay, so the risk of that flood has increased by a factor of 3 or so. Next one. And you can illustrate why that is quite simply with this diagram, which shows all of the storm surge values that have been observed at New London since the onset of the tide gauge in the 30s. And the level of 4 feet has been exceeded 5 times. Next one. But if mean sea level was 20 inches higher, and the weather had been the same over the last 80 or 90 years, then that level would have been exceeded 48 times, so this just illustrates clearly why small changes in the mean value of sea level impacts the probability of a storm surge a lot. Basically, the tails of the distribution change a lot for a small change in the mean. And Marc illustrated that with temperature too. So these changes in the mean, which are quite robust, I think, they have strong implications for the impacts. Next one. Oh, one more. Okay, so here's a brief summary. Oh, let's go back to the summary again. Thanks.
Yeah.
I want to wind up. Well, so what we found, and it's consistent with what we published or what Angie Seth's report showed in 2019, that we should expect higher maximum minimum daily temperatures in both seasons all across the state. I think we've got better resolution of spatial variability in that. The daily minimum temperatures will be changed by mid-century. The downscaled CMIP6 projections really don't provide enough evidence for us to enact or take action beyond what we knew already based on data. But for the water level, it's going to continue to increase, but we don't have strong evidence to change the projection that was made in 2018, that the upper bound of what's possible by 2050 is 20 inches. And it's unlikely that it's going to be less than 20 inches by 2100, and that was true 5 years ago too. Small changes to the mean temperature significantly affects the frequency of extremes. And these have a wide range of practical implications, and we'll probably be able to list some of them. And I'm hoping that the audience will be asking questions about others that they think might be important that we can help develop in the future. Okay, let's wind up here. Thanks everyone for participating. And do we have any questions, Nicole?
Yeah, so just as there's no questions in the chat right now. So just as a reminder, if you do have questions, please enter them in the chat and we'll read them off. I don't know, Marc or Jim, do you want to mention anything about the report? There will be a report on these findings, correct? Yeah,
sure. We're working on that. It will be a document, and we want to, before we finish off, we want to incorporate any information that we receive from this informed audience. We met with some other state agency representatives already, and we're going to hear from some other experts in the near future. And we're hoping that there'll be a report that will be drafted and submitted in the next few weeks.
Okay, great. Yeah, and once that report is published, we will be adding it to our monthly newsletter, the Resilience Roundup. So if you want to keep apprised of when that comes out, I'm going to put that in the chat right now. But we do have some questions coming in. Anna, Amanda Kennedy, how do your findings inform interpretation of current flood map geographies?
Okay. Yeah, we have no evidence with which to change the information supplied by NOAA at this time.
Okay.
Does that answer it?
Yeah, nice and concise. From NOAA, apologies if I missed this, but can you clarify expected changes in precipitation? We are not able to make any more detailed statements about localized precipitation changes, but what are the expected regional changes?
Right. Yeah, it's a great question, and I struggle to convey clearly sometimes. There's convincing evidence that at a regional scale, we will see an increase in average precipitation, but that increase to the average is coming from more extreme days of precipitation or more extreme precipitation events, and actually potentially fewer sort of average rainy days, right? So more severe extreme rainfall and fewer days of average rainfall. And there's convincing evidence for that at a regional scale. We also understand the mechanisms of those changes fairly well. Warmer atmosphere, our temperature projections are good and reliable. Warmer atmospheres can hold more moisture, and so we're fairly confident of that at the regional level. Again, I defer to some really good work that's been done by the likes of Rob Nazarian and Angie Seth, showing this for the regional scale. So it's going to happen somewhere. The question that we were hoping to answer is it going to happen over your, grocery shop versus your neighbor's yard? And at this point, we can't discriminate at that level yet. It's going to happen somewhere. We can't show objectively that it's going to happen over your house. And so it comes down to your appetite for risk mitigation, I guess, at this point is what I would say.
Yeah, let me just add to that this question has been asked all around the world. Can global climate models inform decisions about precipitation at the local scale? And our assessment for Connecticut, which is really what we focused on because no one else had, is the answer is no. That we have to rely upon the data that has been accumulated over the last 100 years, some of which is short and is not uniformly spread across the state. And so we can't do any better than what NOAA has done. Now they're releasing a new analysis in the near future, and we're going to continue to try and assess available information or science as it evolves to see if we can make better predictions for what's the worst case in Connecticut's going to be. But at the moment, the answer is stick with the NOAA result.
All right, thank you. We have another question from Amber in the chat. How will decreases in funding and staffing for national climate research and weather station resources impact future analysis and reporting for Connecticut?
It's one reason that we're not able to answer the question about precipitation is that the data that's available is inadequate. That there are too few long-term, high-quality precipitation observations, and to the extent that those are in danger, that would make things worse. All we need is more. But at the moment, it's unclear how much priority the new administration is going to place on maintaining and expanding the observation network.
To add to that, the measurements is a crucial aspect because it tells us, whether we're getting it right or not. But another crucial aspect is the climate projections themselves. And so we don't run the climate projections. We're simply analyzing the information that they produced. But any threats to people like NCAR, UCAR, Boulder, Colorado, NOAA, people that are running and producing these climate projections and doing so at fine and spatial scales all the time, that would be potentially harmful. The good thing about that is that this is a truly global effort. So there will always be climate projections and there will always be improvement in climate projections. But of course, it's always better if you produce them locally because you have an inherent interest of getting it right here.
Yeah. Thanks. Next question, Marc Mitchell. Do you have a prediction on droughts and wildfires?
No.
Short and sweet. Okay, next, Jody, can you elaborate on the last bullet point about flooding in 2100 only being due to high tides?
Yeah, let me take that one. So this refers to coastal towns. The mean sea level change will affect the flood, the return interval of all levels, and in Connecticut, the way the topography is, the areas that are in the 100-year flood zone right now are vulnerable, and mean sea level won't expand those very much because the coastal topography is very flat near the shore, and then it slopes up rapidly away from the shore just because of the geological history of Connecticut. And so if you plot what the 100-year flood zone is going to be in 2050 with assuming a 20-inch or 24-inch mean sea level rise, it doesn't expand very much. But consequently, the impact of sea level rise is not to expand the floodplain so much along the shoreline, but rather just increase the frequency with which flooding occurs. And when flooding occurs, for any particular return interval, the water level will be deeper.
All right, thanks, Jim. We've got a question from Robert. Do we have any idea of the magnitude of extreme precipitation events regionally? Is it 10 times greater or less?
No, it's not 10 times greater in magnitude or frequency, but I don't want to give a number without being clear in my mind of exactly what it is. So I am happy to link some papers. I've mentioned the authors, Rob Nazarian and co. They've done that analysis. I don't have the number out right now.
We focused this analysis on whether or not we could say anything about Connecticut rather than the region. So there are several papers recently that address regional scale predict changes, and then there is a NOAA effort underway to revise their precipitation forecasts for the purposes of designing flood mitigation measures inland.
Response to that was fair enough. John Trzynski asked, can you explain how you define region in the case of precipitation extremes?
Yeah, that's a great question. And there are a lot of people who have thought a lot harder and longer about this specific question than I have. One answer is that the definition of the region changes quite materially between different papers and studies. So some studies report the US Northeast as being 8 states, others report the US Northeast as being 13 states. I think, Jim, correct me if I'm wrong, but NOAA defines certain zones, and those zones are sort of geographical borders and not any sort of geophysical borders, which might be defined in how the geophysics works and where systems move and where and how weather patterns move. So it's hugely changeable.
So let me just jump in on that. Like the National Climate Assessment, for example, treats the Northeast as being from like West Virginia to Maine and west to western New York. But it's pretty clear from precipitation observations that the contours of high precipitation don't really align well with those geographic boundaries. But the policies are enacted by states. So the motivation, I think, for the federal government was to try and provide information that would be actionable by states. Unfortunately, Connecticut is pretty small compared to that definition of regions. So the statistics across the region are biased to the rest of the area and not so much us. And that was part of the motivation for our study. Looking at the data, it seems to me that the regional precipitation estimates are higher than might be applied just to Connecticut. And so it's probably worthwhile to further analyze what we can say about Connecticut, because we may be overbuilding, and that's the danger of uncertainty. Is if you want to be careful, you want to take the upper bound of what's likely. But if that is biased high, then you might not be spending money as efficiently as possible for resilience measures. Yeah, sorry, that's a vague answer, but the question really depends upon which study is defining the region.
Thanks, Jim. Amanda is asking whether you still find higher impacts to eastern Long Island Sound and western Long Island Sound in terms of flooding frequencies.
Yeah, that's a good question. Thanks. Someone's read the report very carefully, a previous report very carefully. So that diagram I showed earlier with the return interval for New London is slightly different shaped in the western Long Island Sound than it is eastern Long Island Sound. And so for the same change in mean sea level, the change in the return interval is bigger in the western sound than it is in bigger in the eastern sound than it is in the western sound. And that's going to remain the same. I think that's the question Amanda's asking. That result is still true.
Okay.
Great. Thanks, Jim.
Yeah.
I think that's all we've got in the chat so far. I wanted to go back quickly to Dr. Mitchell's question about the droughts and wildfires. I know this isn't something that the two of you have covered. Do you have recommendations for where to look to other scholars or resources related to droughts and wildfires?
Well, the question of wildfires in Connecticut is really quite new. There is data on the frequency of wildfires in Connecticut. I learned last year. We haven't analyzed it. But there is also some regional analysis of the likelihood of drought in the Northeast. And there are papers, for example, that analyze the models that Marc showed the results from for things like number of consecutive days with no rainfall. And those papers, I think, might be the best we can do at the moment. There is one of the things that makes a difference to droughts is the evaporation rate. So it's not just about precipitation; it's about the evaporation rate as well. And as Marc said, we don't have much data on or we don't have great data on the specific humidity and changes in the atmosphere in Connecticut. So we didn't really pursue that very well because we couldn't select which models would be best. But others have, and I think it'd be a good idea for us to include in our report some comments and data and information sources on those issues. And that's exactly one of the reasons that that's exactly the reason we wanted to have this webinar, to get people's questions about what would be valuable.
Okay, great. Well, that's all the questions from the chat. And we're at the hour. So again, thank you all for attending. I am going to put Marc and Jim's email addresses in the chat. If you have any questions that you didn't get to put in the chat, please feel free to email them. So again, thank you all for being here, and we're going to end the webinar. Thank you.
Thank you.